Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at ensemble averaging. In other words, we're going to be looking at averaging our random processes by looking across the ensemble. In order to do that, we first need to say a few words about probability density functions. So let's let x of t be our random process. And sometimes I will designate that as R, capital RP, random process. Well, this, as we saw in the last lecture, this is going to be known as our first order probability density function. That's our first order probability density function. There's lots of things that we can do with the probability density function, just like we've done lots of things with probability density functions when considering random variables. One of the things we could do, for example, is we could integrate from x1 to x2 we could perform that integral. We could integrate our first order probability density function between x1 and x2, and what that would tell us is this equals the probability that this is the probability that my random process falls between limits x1 and x2 at time t. Okay? That's the probability that my random process takes on a value somewhere between x1 and x2 at time t. Alright. Well, we can also look at higher order probability density functions. We're only going to look at the second order probability density function. And before I do that, we'll recall joint PDFs from our discussions of joint random variables. Recall from joint random variable alright, remember we had something look like this. That was a joint PDF. It was a joint probability density function, and we could do things like this. We could integrate from x1 to x2, it's supposed to be an x, and y1 to y2 of my joint PDF. And this was the probability that x1, that random variable x was between x1 and x2. And simultaneously y was between y1 and y2. All right? We've seen that before. Joint probability density function, if we integrate between x1 and x2 and simultaneously between y1 and y2, we get the probability that random variable x is between x1 and x2, and at the very same time y is between y1 and y2. So let's extend that concept to a random process. We're going to let x1 be a random variable, which is my random process at time t1. This is a random variable. If I take a random process and I examine it at a specific instant in time, I come up with a random variable. So x1 is a random variable, and that is my random process evaluated at a specific instant in time. And I'm going to let x2 be my same random process examined at a different instant in time. And then what I'm going to do is I'm going to pretend I have a joint probability density function that looks something like this. I've got a joint probability density function for my random process evaluated at two specific instances in time. This is what would be known as a second order PDF for my random process. And so, for example, what could I do with that? I can integrate x1a, x1b, integrate x2a, x2b of my I can do that. I can perform a double integral over my second order probability density function, and what this tells me is the probability that, let me just write it down, then I'll discuss it. X2a rather. Alright? So if I have a joint or a second order probability density function for my random process x of t, and I perform this integral, which looks a whole lot like something you have seen in the past, what that tells me is the probability that at time instant t1 my random process falls between x1a and x1b, and at the same time, simultaneously, at time instant t2 my random process lies somewhere between x2a and x2b. Alright? Strictly speaking, to fully specify my random process, I would need to look at third, fourth, fifth, nth order probability density functions, and we're just not going to go there. We will not, in this course, go higher than second order PDFs. Okay? All right. Now that we have some idea about probability density functions for random processes, we can start talking about ensemble averaging. Ensemble averages imply that we are looking across the ensemble. Typically when I draw out sample functions, I'll stack them on top of one another, and the time axis will go horizontally from left to right. Looking across the ensemble means I'm going to be looking vertically across the ensemble. So ensemble averaging is performed by looking across the ensemble. Looking across the ensemble. And we're going to look at some first order and second order ensemble averages. We'll start with first order. All right. So remember earlier we talked about a function of a random variable is another random variable. Likewise, a function of a random process is another random process. So if G is a function of a random process x, This is another random process. Oops, RP. All right. A function of a function is a function. A function of a random variable is another random variable because random variables are functions. A function of a random process is another random process. G of t is a function of random process x of t. The expectation, this is directly analogous to what we did earlier on when we talked about random variables. The expected value, or the expectation of g of x of t is integral from minus infinity to infinity g of x times my first order PDF for my random process. All right? In general, after I perform this integral, I'm performing my integral with respect to x. I'm performing that integral with respect to x. And integrating from minus infinity to plus infinity means I'm doing a definite integral. Anytime I do a definite integral, if I do a definite integral against a specific a variable, in this case little x, I lose that random variable in the result. However, the time variable might be preserved. So in general, this expectation of function of x is a time varying function. All right. In general, after I perform that integral, my result is a function in time. All right. So we're still talking about first order ensemble averages. Let's talk about some special cases. Special cases. If my function of x is just x itself, or x squared, then what we're going to find is mean and mean squared values. So the expected value of x of t is going to be integral from minus infinity to infinity of x times this. And strictly speaking, I perform this definite integral against x, time is preserved, and we know that this is the mean, and strictly speaking, it could be a function of time. So this is the mean of the random process. That's the mean of the random process. Similarly, the expected value of my random process squared equals minus infinity to plus infinity x squared times my first order probability density function. Oops. I need time for x first. And this is the mean squared value. And strictly speaking, that could also be a function of time. And likewise, we could find the variance. The variance is, strictly speaking, going to be a function of time. And that is just my mean squared value minus the square of the mean, just like when we worked with random variables. The relationship between the mean squared and the mean value when we determine the variance for my random process is identical to the result we had when we were talking about random variables. Okay? Mean squared, random variable. Or mean squared, and variance. All right. Now, let's talk about second order ensemble averages. And we're going to talk about one in particular. It's going to be known as the autocorrelation. We'll get there in just a second. So, second order. All right. Remember this. Recall from joint random variable discussions. If we had a function g of random variable x and random variable y, this was a double integral from minus infinity to plus infinity of g of x comma y times my joint PDF. All right? That was the way we found the expectation of a function of joint random variables. Okay? For random processes, once again, let's let h, let's change the letters, we'll let h be a function of random process x at time 1 and time 2. So when I take a random process and I evaluate it at a specific instant in time, I get a random variable. So I'm going to let random process x evaluated at t1 be random variable x1, and I'm going to let that a random process x evaluated at t2 be random variable x sub 2. All right. So just like when we, just like on the previous page, the expected value, and by the way, I should say this is a function. This is a function of random process x of t at 2 instances in time. Okay? H is a function of my random process x at 2 separate instances in time. So the expected value of h need to close my parentheses. By direct analogy to the joint random variable result on the previous page, we have double integral from minus infinity to plus infinity h x1 x2 times my second order PDF. That's what that is. All right. Now you'll notice here I'm also performing a definite integral, and I'm integrating against x1 and x2. My result can be a function of t1 and t2. So my result Always keep that in mind. When I perform a definite integral against a variable, I lose that variable in the result. I'm performing definite integrals here against x1 and x2, so that doesn't show up in the result. But I'm not doing anything with x1 and x2, so that can be preserved. All right. Okay. Let's look at a special case. Still talking about second order ensemble averages here. My special case is going to be that H my function of my random process evaluated at 2 instances in time is just going to be the product. Okay? All right. Let me refer you back to something we saw earlier on. We had a thing called the correlation. When we were talking about joint random variables, we had an expectation that was a special case. And we call this thing the correlation. All right, go back and check your notes. When we performed this particular integral, we took my function of x and y was just simply the product of x and y. And I performed that integral by multiplying from minus infinity to plus infinity for both x and y of x times y times the joint probability density function. I got a result, and we called that result the correlation. We didn't develop that in too much detail. We used correlation to calculate correlation coefficient, and we talked quite a bit about correlation coefficient. We're going to extend the concept of correlation now to random processes, and we're going to develop that concept fairly completely. So now what we're going to have is we're going to have a correlation term. It's going to be only of my one random process, but my integral can be, my result can be a function of time t1 and t2, as we saw earlier, minus infinity to plus infinity, x1, x2, times my second order Right? So my function now is simply the product of random process x evaluated at both t1 and t2. Once again, I'm integrating against x1 and x2 from minus infinity to plus infinity. I lose that in the result. I'm not doing anything with t1 and t2, so t1 and t2 can be preserved in the final result. All right. Now, this thing is now going to be called the autocorrelation. Previously we just called it correlation. Now we're going to call it autocorrelation because in effect what I'm doing is I'm comparing a single random process, x in this case, to itself at some other instant in time. All right, turns out, and I'm going to have more to say about this in just a few minutes, correlation, or autocorrelation in particular, is a quantitative measure of the similarity of a random process to itself at a later time. Okay? I'm comparing random process x to itself. That's why we use autocorrelation. Later on, we will talk about cross-correlation when we consider two different random processes at and how they might compare to one another. Okay. Let's do a specific example. Let's let my random process be my handy-dandy random process, which is formed by embedding a random variable inside of a time-varying function. This is a random variable uniform on 0 to 2 pi. So this guy's PDF, that's a lowercase theta. This is, the random variable is always designated with a capital letter. The specific values of my random variable are designated with a lowercase letter. So my capital theta here is going to be with the bar clear through it. So that's going to look something like this. And the peak value will be 1 over 2 pi. And of course the area of that probability density function is exactly 1. We're going to look at this a lot. All right. Notice that my random process is a function of a random variable. That's going to allow us to simplify things a lot. My random process, x of t, is a function of random variable, capital theta. Okay? And what we're going to do is we're going to find the mean and autocorrelation for x. So first thing we're going to do, find the mean value of my random process x. So my mean value is just the mean of a function of random variable theta, and that can be written as g of theta times the probability density function for theta. Okay? The expected value of a function of a random variable is the function times the probability density function for that random variable integrated over all possible values. Yes, I am still dealing with a random process, but because in this particular case I notice that my random process is a function of a random variable, I can simplify my analysis. All right? This is integral from 0 to 2 pi g of theta times 1 over 2 pi d theta. And this is 0 to 2 pi 1 over 2 pi a cosine omega naught t plus theta d theta. And so with respect to my integration variable theta, omega naught and t are constants, and I know over a phase variation of 2 pi radians, my cosine function is half of the time positive and half of the time negative, so my integral here is exactly 0. All right? My random process, the mean of my random process in this particular case is exactly 0. Mean of the random process is 0, always, for this example. Okay? My random process is just a cosine function with a random phase. But I don't care what that random phase is. If I integrate over 2 pi radians, I get 0. Right? It's half the time positive, half the time negative. So next thing I want to do is I want to find the autocorrelation. All right. So what I'm going to do this is I'm going to let T1 equal some arbitrary time point T and T2 equal T plus tau, some time difference parameter, okay? All right. So H of theta is just going to be x of t times x of t plus tau, and the expected value of h is the expected value of x of t times x of t plus tau. And what we're going to find is this is going to be integral from minus infinity to infinity of h of theta times the probability density function for theta d theta. And we're doing this once again because my random process in this particular example is created by embedding a random variable inside of a time-varying function. So my random process is a function of my random variable. All right, so let's do the math. And this is going to be my autocorrelation, R sub x. So let's put this all in. All right, so 1 over 2 pi is this 1 over 2 pi right there is my probability density function for random variable theta, and it has value between 0 and 2 pi. And then what I've done is I've multiplied x of t times x of t plus tau. All right, let's perform this. I'm going to get an a squared over 4 pi, integral from 0 to 2 pi, cosine, cosine omega naught tau plus cosine 2 omega naught t plus omega naught tau plus 2 theta d theta. All right, and I have used, to this point, I've used an identity, cosine A cosine B equals 1/2 cosine A minus B plus 1/2 cosine A plus B. That's how I got to that point. All right. Now, notice this. My first part of my integrand, this part right here, is not a function of theta. However, my second piece of my integrand is a function of theta. So my second cosine function inside of my integral goes through 2 pi 2 times. All right? This second integral, the second piece of my integrand integrates exactly to 0. It goes through 2 full cycles when little theta goes from 0 to 2 pi. All right, that term integrates to 0 since it goes through 2 full cycles when little theta goes from 0 to 2 pi. All right, and then we go to the next page, and our result ultimately is all right, you'll notice that this is not a function of time, but only the time difference parameter tau. Only a function of the time difference parameter tau. All right. And in fact, my autocorrelation looks like this. That's a tau axis. This is my autocorrelation as a function of tau, and it looks something like this. Right? That's 0. This is capital T over 2. This is T. This is minus T over 2. This is minus T. T is the period. It's the period of the random process, and it equals 2 pi over omega naught seconds. All right. And so let's make a couple of observations here. Remember, my random process x of t was a cosine omega naught t plus random variable theta. My autocorrelation is periodic with the same period. All right, that's very important. If I have a periodic random process, my autocorrelation is also going to be periodic with the same period. All right, another thing. This is really very important. I want you to spend some time thinking about this. Autocorrelation, I said this earlier, but I didn't write it down. I'm going to say it now and write it down. Autocorrelation is a quantitative measure of the similarity of a random process to itself at some later instant in time. I should strictly speaking say later or earlier. All right. The point here is that autocorrelation is a quantitative measure. It's a number or a function. And it is a quantitative measure of the similarity of a random process to its shifted self, to itself at a later instant in time. So, if we look up here, when my shift parameter here, or delay parameter, tau, when tau equals 0, my autocorrelation is at its peak. My autocorrelation function is at its peak. And 1 period later, I'm back at the peak. 1 period in the past, I'm at the peak. A half a period into the future or a half a period into the past, I'm exactly dissimilar. Right? I'm 180 degrees out of phase. I'm exactly dissimilar. If I go forward 3 periods, 4 periods, go back in time 3 periods, 4 periods, I am exactly similar to my shifted self. All right, does that make sense? All right. Autocorrelation is a quantitative measure of the similarity of a random process to itself at a later or earlier time. Very important concept. So, let's talk about autocorrelation a little bit more generally now. Autocorrelation, strictly speaking, for our process here, is the expected value of x times x at a later instant in time, tau. All right? And I guess I should write it down. I'm still working on the same example here. All right. The autocorrelation, the autocorrelation evaluated at 0 is the mean squared value. All right, this is the mean squared value Right? When we talked about random variables early on, we saw that the mean squared value of a random variable was the normalized power. Or the RMS value squared. All right? Check your notes. Go back and look. We saw that the mean squared value of a random variable was also known as the normalized power. And we also saw that that was the RMS value of that random variable squared. Well, recall this. If I have any sinusoid, regardless of what the start phase and regardless of what the frequency is, then the RMS value for x equals what? A over square root of 2. So the RMS squared value equals A squared over 2. All right? Autocorrelation is going to be a very important concept for us because of this in part. Autocorrelation is not only a function which gives us a quantitative measure of the similarity of a random process compared to itself at an earlier or later time. If I evaluate the autocorrelation at 0 shift, I get the mean squared value or the normalized power. Very, very, very important. Okay? Well, that's all for today. As usual, if you have any questions about what I've done, please contact me at your earliest convenience and I'll answer any and all questions as fully as I am able. Have a nice day. Bye-bye.